Hey YouTube, this is an advanced tutorial on hardware implementation of one-wire interface of DHT22 with 2 timer and 2 DMA channel of STM32 F103C8. This MCU does not have a dedicated peripheral for one-wire interface, but you can implement it with timer and DMA. DHT22 pin 1 is VCC, which is 3.3 to 5.5. Pin 2 is data pin, which is pulled up with 1K resistor and can't be connected to VCC by MCU or sensor. Pin 4 connect to blue pill ground. To initiate reading temperature and humidity, MCU has to connect data pin to ground for at least 1 millisecond. Then MCU has to release the bus. After that, sensor gonna connect the bus to GND and then releasing it. This is sensor start pulse. Then sensor sends 40 pulse that represent 40 bits that consist of 16 bit of humidity, 16 bit of temperature and 8 bit of checksum. Most significant bit is sent first and sampling period is at least 2 seconds. Whether a bit is 1 or 0 is determined with the pulse on time. If on time is 70 microsecond, bit is 1. If it's 26 to 28 microsecond, bit is 0. Before I talk about the plan, I want to tell you what will you find in other YouTube videos on interfacing DHT22 with STM32. Lots of time you see tutorials on interfacing devices with STM32, it is just modified Arduino codes. This part of code is responsible for MCU init pulse. At the start, pin is set to output, then pin status is changed to ground, then we have a delay, after that pin is set to 1, another delay, and after that pin is set to input configuration. This is called software implementation. When you're doing software implementation for doing anything, you have to write code which CPU has to run. For receiving 40 bits, there is a similar code. In this method, CPU is busy from start to finish and can't do anything else. This is very problematic when MCU has lots of things to do. This is a hobbyist method and it's not suitable for real-world application. Alternative approach is using great capabilities of timer and DMA in STM32. I'm gonna do this project 3 times. In final method, at the end of each measurement, there is just one interrupt and it's all the CPU load we have with this method. Timer and DMA are going to take care of everything. In first hardware implementation method, I'm using timer 3 to generate an interrupt every 3 seconds, which is the sampling period. It should be at least 2, I did 3. In timer 3 update callback function, I start timer 4 in OPM mode, 1 pulse mode. It means after timer 4 counter overflowed 1 time, it's stopped. Timer 4 channel 3 is connected to sensor data pin and it's configured in alternate function open drain mode. It should never be in push-pull mode because MCU should not be able to connect data pin to VCC. Channel 3 is in PWM mode and it's responsible for generating MCU start pulse. To measure on time for 40 pulses, I am using timer 4 channel 1 and 2. Both of them are connected to channel 1 input, which is connected to sensor data pin. In rising edges, CNT value is captured in CCR1 and in falling edges in CCR2. Interrupt for CCR1 is activated. It means whenever there is a falling edge, there is also an interrupt. CCR1 and CCR2 registers value is collected in CCR1 callback function. Next step is ARR and PSC calculation for timer 4. First, I have to decide values for 2 parameters, counter period and CNT clock period. Then calculate ARR and PSC registers value with these 2 functions. Counter period is 1 plus ARR times CNT clock period. Period of CNT clock is duration of 1 step. Duration of 1 step times number of steps is the clock period, the green thing. This is formula for calculating ARR register. Second formula is frequency of CNT clock is frequency of PSC clock divided by 1 plus PSC. This is PSC clock and this is CNT clock. And prescaler clock frequency is 72 MHz. It's internal clock. And frequency of CNT clock is 1 divided by period of CNT clock. So prescaler register value is 72 MHz times period of CNT clock minus 1. Each time timer 4 starts counting, a sampling starts. I want a measurement which consists of MCU start pulse and sensor start pulse and 40 bits of data to fit in a 1 timer 4 cycle. So timer 4 period should be bigger than 1 measurement maximum time. and one measurement maximum time is host pull load time, which should be 1 millisecond minimum, and I do 5 milliseconds. So 5 millisecond plus this is 40 microsecond plus 80 microsecond for sensor pulls load time, 80 microsecond sensor pulls up, and there are 40 pulses for 40 bits. Because I want to calculate maximum measurement time, all bits are considered 1. So the on time is 70 microsecond and 50 microsecond for load time. The result is 10 millisecond, and counter period should be bigger than this. Next question is what should be the value for CNT clock period. This is the smallest time we're going to be able to measure with this timer. So the smaller the better. But I'm not gonna choose the smallest value. I want it to be 1 microsecond because sensor on time is 70 or 26 to 28 microsecond, and 1 microsecond is good enough resolution to measure this range. In the first formula I put maximum value for ARR because I don't have a max limit for counter period. So counter period is 65 millisecond, which is bigger than 10 millisecond. With the second formula for CNT clock period to be 1 microsecond, PSC register value should be 71. This is the starting point. There's a project named DHT22. It has CMCs. In each system init function, priority grouping is set. SysTick is configured. SysTick priority is set. Power and AFIO peripheral are enabled. And this is configuration for pin PO13 and pin PO14. And in each clock init function, clock is set to 72 MHz. Right click on lib folder, click new file, name it DHT22.c. Another time right click new file DHT22.h. In DHT22.h add include general.h. General.h is just CMC's IT header file and system header file. Add DHT22 inclusion in DHT22.c and in main.c. In DHT22.h add hash pragma once. In DHT22.c, write a function with return type of void. I name it DHT22 init. Input argument is void. First step is GPIO configuration. Pin PB8 is timer 4, channel 3, and pin PB6 is timer 4, channel 1. And this is with no remap. As you can see here, timer 4 remap bits. When we have no remap configuration, timer 4 channel 1 is pin PB6 and timer 4 channel 3 is pin PB8. Both of these pins are on GPIO B peripheral, so bit IOPBEN in APB2ENR register should be set so we can use GPIO B peripheral. RCC arrow operator APB2ENR register bitwise or assignment RCC APB2ENR IOPBEN. Set IOPBEN in APB2ENR register to enable GPIO B peripheral clock. Pin PB8 should be in alternate function open drain mode. It should never be in push pull mode because in push pull mode output pin is able to be connected to VCC and it should never happen to one wire bus. Pin PB8 is connected to sensor data pin, and sensor and MCU can't be able to connect data pin to VCC. Pay attention, in datasheet it says timer output pin should always be push-pull, but this is not that case. Here output pin has to be open drain. So mode 8 should be 10, so we have output mode with max speed of 2 MHz, and CNF8 should be 11, so we have alternate function output open drain. GPIO B arrow operator CRH register bitwise and assignment with not of bit mask. GPIO CRH mode 8. Here I cleared 2 bits of mode 8. In the next line, GPIO B arrow operator CRH register bitwise or assignment for setting bits. CNF8 should be 11. So all 2 bits should be set to 1. Here I write GPIO CRH CNF8. So I set 2 bits of CNF8. Mode 8 should be also 10. So bit 1 of mode 8 should be set. GPIO CRH mode 8 bit 1. Pin PB6 should be floating input, so mode 6 should be 00, so we have input mode, and CNF6 should be 01, so we have floating input. In GPIO B CRL register, GPIO B arrow operator CRL register bitwise and assignment with not of bit mask. GPIO CRL register mode 6 or GPIO CRL register CNF6. Mode is 00 and CNF is 01. GPIO B arrow operator CRL register bitwise or assignment GPIO CRL CNF 6 bit 0. Now CNF is 01 and mode is 00. GPIO configuration is done. Now we go to timer 4. First we have to enable its clock. Bit timer 4 EN should be set in APB1 ENR register. RCC arrow operator APB1 ENR register bitwise or assignment RCC APB1 ENR timer 4 EN. Now timer 4 peripheral clock is enabled. For timer 4 to be up counting, CMS and direction bits should be cleared. In this line I clear CMS and direction bits in CR1 register. To clear bits you do bitwise and assignment with not of bit mask. Then I have to set bit OPM in CR1 register to enable one pulse mode. It means counter stops counting at the next update event. For this project it means counter is going to count just one time. Timer 4 arrow operator CR1 register bitwise or assignment timer CR1 OPM bits should be set to 1 so one pulse mode is enabled. ARR has the maximum value and PSC is 71. Timer 4 arrow operator ARR register assignment casted uint16t and it's the maximum value. Timer 4 arrow operator PSC register assignment uint16t and the value is 71. Next step is configuring channel 1 and channel 2 in input capture mode in timer 4 peripheral. Both channel 1 and channel 2 are connected to channel 1 input which is TI1. So CC1S should be 01. It means CCR1 is connected to TI1 and CC2S should be 10. It means CCR2 is connected to TI1. CC1S and CC2S are in CCMR1 register. Here I write timer 4 CCMR1 register bitwise and assignment with not a bit mask. In this line I want to clear bits CC1S and CC2S. In the next line bit 0 of CC1S and bit 1 of CC2S are set. So CC1S is 01 and CC2S is 10. In the next step we have to configure we want capture to be done on falling or rising edges for channel 1 and channel 2 of timer 4. CC1P in CCER register should be 1 because I want CCR1 to capture CNT value in falling edges. So timer 4 arrow operator CCER register to set bit bitwise or assignment with bit mask. Timer CCER CC1P bit is set. CC2P bits in CCER register should be cleared because I want CCR2 to capture CNT value in rising edges. Timer 4 arrow operator CCER bitwise and assignment with not of bit mask for clearing bit CC2P is cleared. Next step is configuring timer 4 channel 3 in PWM mode. This is PWM mode 1 and this is PWM mode 2. This is what I want. In the start of each timer 4 period I want the low time and this is mode 2. And CCR3 register should be 5000 because I want the load time to be 5 millisecond and 5 millisecond divided by 1 macrosecond which is duration of each step. 1 macrosecond duration of each step. 5 millisecond divided by 1 macrosecond is 5000. Timer 4 arrow operator CCR3 register casted 5000. Next step is enabling preload in CCMR2 register. OC3PE bit should be set to 1. So preload for channel 3 is enabled. Timer for CCMR2 register bitwise or assignment for setting bit. Timer CCMR2 OC3PE. So preload for channel 3 is enabled. Next step is configuring channel 3 in output mode. So CC3S bit in CCMR2 register should be cleared. Timer 4 arrow operator CCMR2 register bitwise and assignment for clearing with not of bit mask. Bits CC3S are cleared. But when you're enabling preload for a channel, that channel could not be in output mode. So before enabling preload, I set all CC3S bits so it's not in output mode. Then I enable preload, then it's in output mode. For channel 3 to be in PWM mode 2 configuration, OC3M bits in CCMR2 register should be set to 1, 1, 1, 1. So we have PWM mode 2 configuration for channel 3. Timer for arrow operator CCMR2 bitwise or assignment for setting bit timer CCMR2 OC3M. All these 3 bits are set. Next step is configuring polarity for channel 3 in CC3P bit in CCER register. I don't want to invert it and it has to be active high. So CC3P bit should be cleared. Timer for arrow operator CCER bitwise and assignment with not of bitmask to clear bit CC3P. In this step, I'm gonna enable channel 1, 2 and 3 by setting bits CC1E, CC2E and CC3E in CCER register. Timer for arrow operator CCER bitwise or assignment CC1E, CC2E and CC3E bits are set. So channel 1, 2 and 3 are enabled. It's good to generate update in the next line. So all configurations are saved. Pay attention if you were using timer 1 or timer 8 which are advanced. Bit MOE has to be set so you are able to use output channels. But I'm using timer 4 and this timer does not have a BDTR register. I want to use update interrupt and capture compare 1 interrupt in timer 4. So bit UIE and CC1IE should be set in DIER register. Timer for arrow operator DIER, UIE and CC1IE are set. Before enabling an interrupt, you have to clear its flag. So I have to clear UIF and CC1IF. Before enabling interrupt, I write timer for arrow operator SR register. I do the assignment with not of bitmask. Why did I do this? Because this is how SR register work in timer peripheral. Next step is enabling these two interrupts in NVIC peripheral. Define a variable of type uint32t, name it priority grouping, assignment, NVIC get priority grouping, control space. I call this function doesn't have any input argument. I save the result to PG variable. In the next line, I use the function NVIC set priority. First input is interrupt number. Timer 4 has one interrupt and its number is timer 4 IRQ number. To write the second input for this function, I use NVIC encode priority. First input of this function is PG variable. Second input is preemption priority. I put 3. Third input is sub priority. I put 0 because we don't have any bit for sub priority. Next step is using NVIC enable IRQ for enabling this interrupt in NVIC peripheral. This function has one input and that's interrupt number. Compile the code. Next step is writing callback functions for update interrupt and capture compare 1 interrupt. Before DHT22 init, I write a function with return type of void DHT22 capture compare 1 callback. Input argument is void and another function for update callback. We specify these two functions as callback functions by writing their addresses in function pointer variables. Before enabling interrupt in NVIC peripheral, write x callback timer 4. This is a structure. Put dot after a structure and you can access its members. Access CC1. This member is a function pointer variable and I store DHT22 CC1 callback function address in this function pointer variable. Remember, name of a function is address of that function. In the next line, I specify callback function for update interrupt. Here, instead of CC1, write UP. UP is a member of this structure and it's a function pointer variable. I stored DHT22U callback function address in this function pointer variable. In the next step, I'm going to write this function. Capture compare 1 interrupt happens every time there is a falling edge on one wire bus. In callback function of this interrupt, we have to calculate the difference between CCR1 and CCR2. So we know the amount of time that bus was released and we figure out the corresponding bit value. If on time is 70 microsecond, bit is 1. If on time is 26 to 28 microsecond, bit is 0. I say if it's bigger than 50, bit is 1. Pay attention, CCR1 and CCR2 value unit is 1 microsecond because CNT clock period is 1 microsecond. In this function, I write if timer for arrow operator CCR1 register minus timer for arrow operator CCR2. If this is bigger than 50, then the corresponding bit is 1. I have to know whenever this function is called what falling edge is responsible for calling it. So I define a variable here of type uint8t. I name it DHT22 loop. And every time this function is called, I do DHT22 loop plus plus. This variable is incremented by 1 whenever this function is called. This is how we know which falling edge we're at. So how many falling edges are there? Pay attention before communication starts. Bus is 1, bus is pulled up, and after communication is finished, bus is pulled up also. So the number of falling edges and rising edges is equal. There is MCU start pulse, there is sensor start pulse, there are 40 bits, and there is an end pulse. And the sum is 43. There is 43 falling and 43 rising edges. There are 43 falling and 43 rising edges. MCU receives 40 bits every time sampling is done. To store 40 bits, I define a variable of type uint64t. I name it double D. In CC1 callback function, if difference between CCR1 and CCR2 is bigger than 50, it means the corresponding bit is 1, and we have to set that bit in DD variable. To set a bit, we do bitwise or assignment with bit mask. To make bit mask, we have to left shift 1 by amount of bit number. Before that, you have to cast 1. Its type has to be uint64t. And bit number is 42 minus DHT22 loop. Pay attention, the first time falling edge happens and this function is called. When we are in this function, DHT22 loop is 0. The second time this function is called and there is a falling edge, when we are in the function, DHT22 loop is 1. So the second time is 1. The third time is 2. The fourth time there is a falling edge. It's when most significant bit is received, bit 39. When we are in the fourth falling edge, the value of DHT22 loop variable is 3. For bit 39, bit mask is 1 left shift 39, and 39 is the bit number. The last bit that is going to be received is bit 0, and bit mask for bit 0 is 1 left shift 0. We can make bit number, which is 39, to 0 with this equation, 42 minus DHT22 loop. When bit 39 is received, DHT22 loop is 3. 42 minus 3 is 39. And when bit 0 is received, DHT22 loop is 42, and 42 minus 42 is 0. Next step is writing update callback function. This interrupt happens at the end of every sampling. Here I have to calculate checksum, which is sum of most significant 4 bytes. I define an array of type uint8t with 5 members. Its name is bytes. Byte 0 assignment DD variable. Byte 1 assignment DD variable right shift 8 times. Byte 2 assignment right shift 16 times. Byte 3 assignment right shift 24 times. And byte 4 is right shift 32 times. Byte 0 is the checksum that MCU received from sensor. And sum of byte 1 to byte 4 is the checksum MCU has to calculate. If sum of byte 1 to 4 is equal to byte 0, it means 40 bits are received successfully. Here I define a variable of type uint8t. I name it CS checksum. Its value is sum of most significant 4 bytes. If CS equals byte 0, it means calculated checksum and received checksum are equal. This is how MCU receives 40 bits. Least significant byte is checksum, after that is temperature, after that is humidity. To calculate temperature in degrees, you have to divide this 16-bit data by 10. And to calculate humidity in percent, you have to divide this 16-bit by 10. Here I define two float variables. This is wrong and you shouldn't do this because this is STM32F1 and float calculation here requires big functions. But this tutorial is not about that, and I define a variable named RH and another one named TMP. To extract humidity from the 64-bit variable, I have to right shift it 24 times. First I cast it, it's uint16t, then dd variable had to be right shift 24 times. Put this in parentheses, divide this by 10. After 10 put dot 0 and an f after that. It means 10 is a float number. And then semicolon. Cast this as float. To calculate TMP, you just have to right shift it 8 times. If checksum is not correct, I wanna write 0 to TMP and RH. There is a possibility here that for whatever reason, if dd variable is 0, then all bytes are 0 and CS is going to be equal to bytes 0. So I put this condition in parentheses. I do and with CS. It means CS variable has to be not 0 and it has to be equal to bytes 0 to condition for this if to be true. Writing callback function is finished for now, and next step is doing configuration for timer 3. Timer 3 is going to be responsible for starting timer 4. First step is enabling timer 3 clock in APB1ENR register by setting bit timer 3 EN. RCC arrow operator APB1ENR register bitwise or assignment timer RCC arrow operator APB1ENR register bitwise or assignment because we want to set bit. I want to set bit timer 3EN in APB1ENR register to enable timer 3 clock. To have an up counting counter, we have to clear bits CMS and direction in CR1 register. Timer 3 arrow operator CR1 register for clearing bitwise and assignment with not of bit mask. Timer CR1 register direction bit and timer CR1 CMS bits. This slide is about calculating ARR and PSC registers value for timer 3. First I have to decide values for two parameters, CNT clock period and counter period. Then with these two formulas I can calculate PSC and ARR. Counter period is 3 seconds. Because I'm using update interrupt and I want to interrupt every 3 seconds. And for CNT clock period I choose 100 microseconds, which is more than enough resolution for this range. So if CNT clock period is 100 microsecond, with this formula PSC register value is 7199, and with counter period 3 seconds, with this formula ARR is 29999. Timer 3 arrow operator ARR register assignment uint16t 29999. Timer 3 arrow operator PSC register assignment uint16t 7199. To enable update interrupt I have to set bit UIE in DIER register. Timer 3 arrow operator DIER register bitwise or assignment for setting bit timer DIER UIE. Before enabling an interrupt we have to clear its flag. Timer 3 arrow operator status register assignment. When you want to clear a flag in a status register you have to write not of bit mask in a status register, and the bit that I want to clear is timer status register update interrupt flag. And before this it's good practice to generate an update event. Timer 3 arrow operator EGR assignment timer EGR UG. Setting UG bit generates an update event. Update event causes values to be stored in registers with preload capability. Next step is enabling interrupt in NVIC peripheral. I use NVIC set priority to specify priority for timer 3 update interrupt. First input of this function is interrupt number. Timer 3 has just one interrupt. Its number is timer 3 IRQN. Second input of this function is priority. I make that with NVIC encode priority. For the first input I write PG variable. This is priority grouping. For preemption priority I write 2. I want a higher priority than this. And for sub priority I write 0 because we don't have any bit for sub priority. Next step is enabling interrupt by NVIC enable IRQ. This function has one input and its interrupt number. It's timer 3 IRQN. And the last thing is a starting timer 3. It's timer 3 arrow operator CR1 register bitwise or assignment timer CR1 CEN. By setting bit CEN in CR1 register, timer 3 starts counting. Next step is writing update callback function for timer 3. Here I write a function with the return type of void. I name it DHT22 timer 3 update callback. Input argument is void. To set this function as callback function for timer 3 update interrupt, we have to write its address to a function pointer variable. Here I write x callback timer 3. This is a structure. You put dot after it and you can access its members. I want to set function for update interrupt callback. I choose up. Then you put assignment and here you write the function name. Remember, function name is its address. I write DHT22 timer 3 update callback function address to this function pointer variable. Timer 3 update interrupt happens every 3 seconds. And in this function, I'm going to start timer 4, so timer 4 does the measurement. Before I continue writing this function, I want to add something to DHT22 update callback, which is update interrupt callback function for timer 4. At the end of this function, add DHT22 loop assignment 0. And also add dd assignment 0. Continue with writing function DHT22 timer 3 update callback. At the start of this function, I want to disable update interrupt in timer 4 because I'm going to generate update event in this function and I don't want interrupt to happen. DIER bitwise and assignment with not of bit mask. Timer DIER UIE. I want to clear bit UIE in DIER register because I want to disable update interrupts. In the next line, I'm going to change CCR3 register. Casted uint 16T. Channel 3 is responsible for sending MCU start pulse, which initiates measurement. And with value of 5000 for CCR3, we would have 5 millisecond load time on one wire bus. CCR3 register has preload capability, so values are not saved in this register unless an update event happens. So I have to generate an update event. Timer 4 arrow operator EGR register assignment timer EGR UG. By writing 1 to bit UG in EGR register, an update event is generated. Next step is enabling update interrupt. Remember, I disabled update interrupt here because I wanted to generate an update event here. And I have to enable update interrupt again in this line. Timer 4 arrow operator DIER bitwise or assignment timer DIER UIE update interrupt enabled. Set bitwise or assignment with bit mask. I want to set bit UIE in DIER register. Next step is enabling timer 4 CR1 register bitwise or assignment timer CR1 CEN bit. When you set CEN bit in CR1 register, timer starts counting. And the most important thing, you have to write 0 to CCR3 register. CCR3 assignment 0. Each of these lines of code have a specific purpose. I want you to stop the code and think about the code that I wrote. Can you guess what I did? In above picture, you see PWM mode 2 when counter is up counting and polarity of output channel is not inverted, it's active high. And in this one, you see PWM mode 2 also when counter is up counting and output is active high, and one pulse mode. One pulse mode means counter stops counting at the next update event. In this picture, counter starts counting here and the next update event is here. And counter stops counting at this update event. After counter stops counting, value of CNT register is 0. In PWM mode 2, when CNT register is less than CCR, which is 5000, output is low. Here output is low because CNT is less than CCR, which is 5000. And when CNT is bigger than CCR or equal to CCR, CNT is bigger or equal to CCR, then output is high. This is the output channel in PWM mode 2 with 5 millisecond low time and 65.5 millisecond high time. This channel is responsible for generating MCU start pulse. When one pulse mode is activated, after timer stops counting, CNT is 0, and 0 is less than 5000. 5000 is value of CCR3. When one pulse mode is activated, after counter stops counting, here channel output is going to be low because CNT is 0 and CNT is less than CCR3, which is 5000. But this is not what I want. I want to generate this pulse, not this one. I want to have a low time of 5 milliseconds every time timer 4 starts counting, and this is the pulse that I want for the output of channel 3 of timer 4, not this one. So how can I achieve this? How can I get this? Solution to this problem is changing value of CCR3 to 0 when timer 4 stops counting. If CCR3 is 0, so CNT is equal to CCR3 because CNT is also 0. So the output would be high, and this is what I want. I want timer 4 channel 3 output to be high after timer 4 stops counting. So in the first cycle, when timer 4 starts counting, CCR3 should be 5000 because I want to generate the low time of 5 milliseconds. But after timer 4 stops counting, CCR3 should change to 0. This is the code that I wrote in DHT22 timer 3 update callback function. When I was writing, I forgot to write this line. I'm going to fix it later. After CEM bit in CR1 register of timer 4 is set in this line, timer 4 starts counting. And all of these lines are before timer 4 starts. In the first line, I deactivated update interrupt for timer 4 because I have to generate an update in this line and I don't want an interrupt to happen because of that. In the second line, I changed value of CCR3 to 5000 because I want to have a 5 millisecond low time pulse. Because CCR3 is preloaded, it means values that I write in this register doesn't save in it until an update event happens. So in the next line, I generate an update event, so value of 5000 is stored in CCR3 register. After you generate an update interrupt flag is set in a status register, so you have to clear it. In this line in a status register, I cleared update interrupt flag. In the next line, update interrupt is activated for timer 4. In the next line, timer starts counting by setting CEN bit in CR1 register, and CCR3 value is 5000. In the next line, value of CCR3 is changed to 0. But CCR3 value does not change right away because it is preloaded, and its value is going to change in the next update event, and next update event is here. After next update event, value of CCR3 would be 0, and this is exactly what I want. In the first cycle, I want CCR3 to have value of 5000. And after an update event, I want its value to be 0. So channel 3 output in timer 4 is not low and it's high. Compile the code, write DHT22 init function declaration in DHT22.h in main.c before while 1, write DHT22 init. Compile the code, go to debug. In live expression view, you can see TMP and RH. Run the code. This is DHT22. As you can see, temperature is 26.3 and humidity is 42.2%. It looks like sometimes we might not get the right data because their value is 0 sometimes, but I'm going to put that to test later. Here you can see if I do this, temperature is 26, 28 now, and humidity is 99%. If I suck the air out, I can lower humidity and temperature. In DHT22.c, define two variables of type AM2302T. One is DHT total, another one DHT damage. In DHT22 update callback, At the end of this function, I increment DHT total by 1. I know this interrupt happens at the end of each measurement. And if calculated checksum does not equal received checksum, it means the received data is damaged. In the else, I write DHT damage. I increment this variable by 1. Compile the code and go to debug. In live expression, add DHT total and DHT damage. Run the code. As you can see, we are getting a lot of damaged data. Go to DHT22.c. There is a line in this function that I forgot to write, and this is its place. Can you guess what that line is? Stop the code and think about it. Timer for arrow operator, SR register assignment, not of timer SR UIF. Before enabling an interrupt, you have to clear its flag, especially when you're generating update the line before that. Compile the code and go to debug. Run the code. As you can see, we have received 5, 6 sampling and just 1 data is damaged. It's really good and predictable because it was the first data that was damaged, and all data after that are received correctly. Temperature is 26.7 and humidity is 37.7%. If I do this, humidity is now 99.9% and temperature is 28.8. I am going to do this project 2 more times, each time with less CPU load. Right click on DHT22, click copy, right click paste. I name it DHT22v2. Right click on DHT22 and click close project. In DHT22v2, click core, source, main.c. Click on project properties. C++ general, path and symbols. I have to correct these 3 include directories. Instead of DHT22, it should be DHT22v2. Apply and close. Right click on debug folder and click delete. Right click on DHT22 debug.launch and click delete. Compile the project. There is no error and warning. In the second way that I'm going to do this project, first thing that is going to change is using union instead of shift operators. Union is a type of variable in C language which all of its members have the same address. Address of a thing is address of its first byte. In this example, address of first byte for 3 members of union are the same. In this slide, I'm talking about Indianness. It's about how things are stored in memory. Data is a 32-bit variable. It occupies 4 bytes. If least significant byte goes to lowest address, it's called Little Indian. Lowest address is first address and is address of data variable. It's address of the first byte that data variable occupies. Little Indian is how things are stored in our computer. Because union members have the same address, you use union when you want to access an address as different types. When bits are being received, I need a 64-bit variable to store 40 bits. This is 64-bit variable in memory. In the first row, you see imaginary addresses. Remember, first address belongs to least significant byte, and the last byte that received from sensor is going to store here. Bit number for the first bit that MCU receives is 39, and bit mask is 1 left shift 39. This is the first bit that MCU receives. For the last bit that MCU receives, bit number is 0 and bit mask is 1 left shift 0. This is the last bit that MCU receives. I also want to be able to access individual bytes to calculate and verify checksum. For this, I need an array of bytes. I named it byte with 5 members. Received checksum is byte 0. Calculated checksum is sum of byte 1 to 4 and it should be equal to byte 0. I also want to have access to 16 bit of humidity and temperature, and this is their place in the 40 bits that are received by MCU. Least significant byte is checksum, after that it's temperature and humidity. Last byte that is received is the byte with the lowest address. It's the least significant byte. It's checksum. After that it's temperature and humidity. To extract these from the 40 bit, I define a structure. First member is a byte named CS, checksum. After that 16 bit of temperature and 16 bit of humidity. But if I define a structure like this, there is going to be an empty byte in my structure. The reason is TMP variable type is uint16t and its alignment is 2. It means it can just be stored in addresses that are divisible by 2. So it can't be stored here because 1 is not divisible by 2, but 2 is. So TMP is going to store here and RH in address 4. Solution for this problem is using attribute packed. You have to write it exactly like this after a struct keyword. Now compiler doesn't care about alignment of TMP and RH anymore. So I want to access one address as 3 different types. To store 40 bits, I want to access this address as a 64-bit variable. To calculate checksum, I want to access this address as an array of bytes that has 5 members. And to read temperature and humidity, I need to access this address as an structure named result with one 8-bit named CS, here is CS, and two 16-bit temperature and humidity. This is why you use union when you want to access an address as different types. Here I'm accessing one address as 3 different types. Go to DHT22 init. In DHT22.c I write definition for a variable type named DHT_type_def. DHT_type_def is a union with 3 members. Data, which is 64-bit, byte is an array with 5 members of type uint80, and result, which is a structure with 3 members. With this new type, I define a variable named DHT_data. Now instead of DD, I use DHT_data. DHT_data is a union. You put dot after union and you can access its members. Now I want to access this address as 64 bits. Next, in DHT22 update callback function, to calculate checksum, I write DHT_data dot. I want to access byte 1 plus byte 2 plus byte 3 plus byte 4. Now I don't need these lines and I don't need byte array. Here instead of byte 0 you write DHT_data byte 0. Instead of doing the write shift 24 times for DD variable, I just write DHT_data dot. Result is a structure, you put dot after it, you can access its members. I want to access 16-bit of humidity. I don't need to do any write shift anymore. Value is in memory and I can access it however I want. And I do this for the temperature also. Here instead of RH, I choose TMP. In the last line of this function, instead of write DHT_data dot, I choose 64-bit type to access this address. Now delete definition of DD variable and compile the code. This was first step toward lowering CPU load. This is callback function for timer 3 update interrupt. This interrupt happens every 3 seconds and this code starts timer 4. In the next step, this function is going to be eliminated and there is no need for timer 3 update interrupt anymore because timer 3 is going to start timer 4 automatically. Timer 3 is master timer and timer 4 is a slave timer. Master timer sends TRGO, trigger output signal. Timer 3 update event is output trigger of timer 3. Timer 4 trigger input comes from timer 3. And this trigger starts counter in timer 4. So instead of having an interrupt in update event and in callback function starting timer 4, timer 3 is starting timer 4 automatically. Every time update event happens in timer 3, timer 4 starts counting and timer 4 is in 1 pulse mode. It means when it reaches update event, it doesn't count anymore. There is another change from the previous project. Instead of using timer 4 channel 3 to generate a start pulse, I'm using timer 3 channel 1. This solves a lot of problems. I want to use timer 3 channel 1. We know remap configuration channel 1 is pin PO6, but I don't want to use that pin. I want to use pin PB4 for channel 1 of timer 3. So timer 3 remap bits should be 10 partial remap. In DHT22 init function, before doing timer 3 configurations, AFIO, arrow operator, map R register, bitwise and assignment with not of bit mask, AFIO, map R, timer 3, remap. I clear 2 bits, timer 3 remap bits in map R register in AFIO peripheral. To set partial remap configuration, these 2 bits should be 10. So in the next line, write AFIO, arrow operator, map R register, bitwise or assignment for setting bit, AFIO, map R, timer 3 remap. I want to set bit 1. So timer 3 remap bits are 10. Pin PB4 is in alternate function open drain mode. Mode 4 has to be 10 output mode with max speed of 2 MHz, and CNF4 has to be 11 alternate function output open drain mode in GPIO BCRL register. In this line I clear 2 bits of mode 4, and in this line I set 2 bits of CNF4 and mode 4 bit 1. So CNF4 is 11 and mode 4 is 10. Next step is configuring channel 1 in timer 3. CCR1 value is 5 millisecond, which is the duration of load time that I want, divided by 100 microsecond, which is duration of one step. CCR1 is 50. Instead of writing configuration for channel 1 in timer 3, I can copy configuration from channel 3 in timer 4. Timer 4 channel 3 is not used anymore, and I can cut this configuration from here and paste it here. Timer 3 CCR1 is 50. I have talked about this configuration before. I'm not gonna talk about it again. For a slave timer, which is timer 4, we have to set in TS bits in SMCR register where the trigger is coming from. Internal trigger 0, 1, 2 and 3 means trigger is coming from another timer. In this example, timer 4 is a slave timer and timer 3 is master. Internal trigger 2 and TS bit has to be 0, 1, 0. Go where timer 4 configuration is. Here is a start of timer 4 configuration. After writing ARR and PSC register values, here I write a slave. In this line I cleared TS bits. To clear bits, you do bitwise and assignment with not of bit mask. And in this line I set bit 1 of TS bits. So TS is 0, 1, 0. Now timer 4 is a slave and timer 3 is master. In a slave timer, which is timer 4 in SMS bits in SMCR register, I said what kind of effect I want this trigger to have on timer 4. I want trigger mode. In this mode, counter starts at rising edge of trigger input. And this is exactly what I want. I want every time timer 3 update event happens, which is master timer, timer 4, which is a slave timer, start to count. In this line, I cleared SMS bits in SMCR register, and in this line, I set bit 1 and bit 2 of SMS bits. So SMS is 110. In master timer, which is timer 3, in MMS bits in CR2 register, we set what is output trigger. If MMS bits are 0, 1, 0, update event is selected as trigger output. Go to timer 3 configuration. After setting ARR and PSC, I write timer 3 master. MMS bits are 1, 0 in CR2 register in timer 3. In this line I cleared MMS bits, and in this line I set bit 1 of MMS bits. So now MMS is 1, 0. Timer 3 channel 1 is not activated yet. I write timer 3 arrow operator CCR register bitwise or assignment timer CCER CC1. When I set bit CC1 in CCER register, channel 1 is activated. There is no need for update interrupt in timer 3, so I can delete these lines. This is enabling interrupt in DIER register, this is for callback function, and this is enabling interrupt in NVIC peripheral. In timer 4 configuration, here there is no need for enabling channel 3 in timer 4. It's not used anymore. And in GPIO configuration, because pin PB8 is not used anymore, I can delete these lines. And DHT22 timer 3 update callback function is not used anymore. Compile the code, go to debug, start the code, I let it work for a while. Every 3 seconds a sampling is done. So since 16 sampling is done and there is no damage data, temperature is 25.5 and humidity is 32%. If I do this, now humidity is 99.9% and temperature is 27.3. If I suck the air, now humidity is 61% and temperature is 25. 31 sampling has done and there is no damage data. To do the project for the third time, right click, copy, right click, paste, name it DHT22v3, right click on DHT22v2, click close project, open DHT22v3, click on core, source, main.c, click on project, properties, C++ general, paths and symbols. I have to correct these 3 directories. Instead of v2 it should be v3. Apply and close. Right click on DHT22v2 debug and click delete. Right click on debug folder and click delete. Compile the project. There is no error and warning. Right click on DHT22 init and open declaration. Now I'm in DHT22.c file. Unattainable goal is that peripheral do everything and there is no need for CPU after peripherals are initiated. As much as I can do, I have to make peripherals do the job, not CPU. And my next target is DHT22 capture compare 1 callback function. This interrupt happens at every falling edge on data pin 43 times in less than 10 milliseconds in each sampling. And there is a sampling every 3 seconds. This is a bad interrupt to have. In this function, for each bit difference between CCR1 and CCR2 is calculated. If it's bigger than 50, that bit is 1 and it's stored in DHT data variable. Instead of reading CCR1 and CCR2 registers values in interrupt, 2 DMA channels can transfer these 2 registers values to 2 arrays in memory. And at the end of each measurement in DHT22 update callback function, I can calculate bit values for 40 bits in just one function. Before using any peripheral, you have to enable its clock. To enable DMA1 peripheral clock, you have to set bit DMA1EN in RCC AHBENR register. At the end of DHT22 init function, before enabling timer 3, here is a place to do DMA configuration. In this line, I set DMA1EN bit in AHBENR register in RCC peripheral. STM32F103 just has one DMA, it's DMA1. I have to figure out what channels I have to use from DMA1 request mapping. DMA1 has 7 channels and each channel is connected to some requests from peripherals. Request from timer for channel 1 is connected to channel 1 and request from timer for channel 2 is connected to channel 4 of DMA. So channel 1 is going to transfer data from CCR1 register and channel 4 is going to transfer data from CCR2 register. Each DMA channel has a CPAR register, its peripheral address register. If you're not transferring data from memory to memory, then one side of transfer is peripheral. It doesn't matter you're reading from peripheral or you're writing to peripheral. You have to write peripheral address in CPAR register. The data that I want to transfer is content of CCR1 and CCR2 register. For DMA1 channel 1, value of CPAR register is address of timer 4 CCR1 register. And for DMA1 channel 4, CPAR register is address of timer 4 CCR2 register. Write DMA1 channel 1 arrow operator CPAR. Assignment address of timer 4 arrow operator CCR1. Compile the code. There is a warning in this line. It says it makes integer from pointer without the cast. This expression is a pointer, and here I'm writing a pointer in an unsigned 32-bit. So here I have to cast it. Its type is uint32t. Compile again, and there is no warning. For channel 4, here you write DMA1 channel 4, and you write address of CCR2 register to CPAR register of channel 4. Next step is configuring CMAR register. This is memory address. In this case, two DMA channels are going to transfer content of CCR1 and CCR2 register of timer 4 to somewhere in memory. In CMAR register, we have to configure where in memory data is being transferred to. Go at the top of this file. Here I'm going to define three arrays of type uint16t. I'm named the first one CCR1 with 43 members. Next CCR2 with 43 members, and one array named diff with 43 members. And write DMA1 channel 1 arrow operator CMAR register assignment casted is uint32t. I want value of CCR1 register transfer to an array named CCR1 that I just defined. Remember, name of an array is address of that array. And for channel 4, you write DMA1 channel 4 CMAR register. I want content of CCR2 to be transferred to CCR2 array. Each DMA channel has a configuration register. It's called CCR. We have to configure CCR register for channel 1 and 4. For both channels, memory to memory is disabled because I am reading from peripheral. For both channels, priority is not important in this project, so I put PL bits to 00 so it's low. M size is the size of data that is being read from memory or write to memory. In this case, M size is the size of data that is being written to CCR1 and CCR2 arrays, and it's 16 bits, so M size should be 01 for both channels. P size is peripheral size. It's a size of data that is being read from or it's being written to peripheral registers. In this case, it's the size of data that is being read from CCR1 and CCR2 registers in timer 4. And it's 16 bits. P size should be 01. Minc bit should be set to 1 for both channels. It means memory increment enabled. Every time DMA writes something to memory, CCR1 or CCR2 array, the next time you don't want DMA to overwrite the previous data. So memory address has to be incremented every time DMA transfers the data. But pink bit for both channels should be cleared because you don't want peripheral address to increment. Always you want to read from CCR1 and CCR2. Circular mode is disabled. For both channel, DIR bit is 0 because I am reading from peripheral, reading from timer 4, CCR1 and CCR2 registers. All three interrupts are disabled, and when you want to enable channel, you have to set EN bit in CCR register. In first step, I clear all bits in CCR register for channel 1 and for channel 4. For both channels, P size and M size are 01, so bit 0 of M size and P size has to be set, and because memory increment has to be enabled, minc bit is also set. Channel 4 configuration is the same. Before I enable channel 1 and channel 4 of DMA1, I have to set number of data to transfer for each channel in their CNDTR register. For number of transfer for channel 1 and channel 4, I put 44. And next step is enabling channel 1 and channel 4 of DMA1 by setting EN bit in CCR register. Then go to timer 4 configuration. Here I have to enable DMA request for channel 1 and channel 2. This is done by setting bit CC1DE and bit CC2DE in DIER register. And there is no need for capture compare 1 interrupt, and it shouldn't be enabled in this line. And there is no capture compare 1 callback function. Now we can delete DHT22 capture compare 1 callback function. In DHT22 update callback function, first you have to disable channel 1 and channel 4 of DMA1 by clearing EN bit in CCR register. Next, write for uint8t I assignment 0, do the loop till I is less than 42, At the end of the loop, increment I by 1. I defined 3 arrays with members of type uint16t with 43 members. I write the equation here: diff assignment CCR1 minus CCR2. For 40 bits, difference between CCR1 and CCR2 has to be calculated, and based on value of that difference, you figure out if that bit is 1 or 0. If bit is 1, you have to set that bit in am_data variable. You do bitwise or assignment, then you caset uint64t 1 left shift a number minus I. I don't want to explain to you why indexes for this array are the way they are, or why the value that is being written here is what it is. So I give you the time to think about what these values should be. Stop the code and think about it. At the end of this function, write the value of 44 in CNDTR register for channel 1 and channel 4 of DMA1. Remember, when you're writing to CNDTR register, DMA channel has to be disabled. In next step, you enable channel 1 and channel 4 of DMA1. Compile the code. There are 2 errors. AD data should be DHT data. Compile the code. There is no error and warning. Compile the code and go to debug. In live expression view, add CCR1 array and CCR2 array and diff array. Run the code. Every 3 seconds a sampling is done. Now 7 sampling is done. There is no damaged data. Humidity is 37.0% and temperature is 22. If I do this, now temperature is 23 and humidity is 99.9%, 14 sampling. If I suck the air out, I can lower humidity and temperature. And now humidity is 55 and temperature is 22. 24 sampling is done and there is no damaged data. In the third part of this video, I used 2 DMA channel. DMA1 channel 1 transfer data from timer 4 CCR1 register to CCR1 array. These are values of timer 4 CNT register whenever a falling edge happen on data pin. DMA1 channel 4 transfer data from timer 4 CCR2 register to CCR2 array. These are values of timer 4 CNT register whenever a rising edge happens. Diff array is the difference between rising and falling edges. This is value of on time for each bit. First on time is for MCU start pulse. Second one is for sensor start pulse. And from the third one, it's the 40 bits. If value of on time for a bit is 26 to 28, like this one's, bit value is 0. If on time is 70 microsecond, like this one's, bit value is 1. This was interfacing DHT22 with STM32 with 2 timer and 2 DMA channel. The only CPU load is this function, and this function is called at the end of each measurement. Every 3 seconds this function is called, and during communication to DHT22, CPU has no job. "95 sampling is done and there is no damage data.